We begin our discussion of cloud physics by examining the physical properties of water. We will attempt to address the three following questions. Firstly, what are the three phases of water? What are the transition between these phases called? And what is the latent heat associated with these phase transitions? We begin by having a look at water, what water looks like on the molecular level. Firstly, in the case of solid ice, the molecules of water are arranged in this hexagonal shape, this six-sided shape. And you'll actually see this shape at the center of every snowflake if you look at it very carefully. That six-sided hexagon. And that arises out of the shape of the water molecule. You'll notice these small circles here, or spheres, represent hydrogen atoms. They're small. And here you have oxygen atoms, which are a little bit larger. If you add a little bit of energy and actually melt the ice over here, you get this sort of semi-ordered molecular structure over here. The bonds between the hydrogen and oxygen atoms begin to break, and the atoms start to move around a little bit more freely. Notice that they still cluster together here, and it's this sort of clustering together of the atoms that makes them a bit liquid, more of a liquid than a gas. Add still more energy to the system, and the molecules start moving around randomly without sticking to each other. Here two are sticking to each other. These are actually colliding. What you would do in the case of a gas is that these would start colliding with a container. So if this were a balloon here, that's what would cause the pressure, the motion of these molecules. So this chart here is an important one to remember because it explains a lot. You have here the three phases of water represented: the solid, the liquid, and water vapor. On top, you see this red arrow indicating that latent heat, or just basic heat, is being added to the water. And if you will do that, you will start by melting anything solid and turning it into a liquid. And if you continue to add energy, it will evaporate into a vapor. If you remove energy from the system, in other words, you release latent heat into the environment, you go in the opposite direction. So water vapor would condense into a liquid. And if you still take more energy away, the liquid will transition into a solid and freeze. Lesser known processes are sublimation and deposition. In the case of sublimation, the phase transition goes directly from a solid to vapor, and that actually happens in the case of a warm summer day and when there's snow on the ground. I actually should correct myself. There's never snow on the ground in the summer. I'm thinking more of the spring here. Now, the opposite process of deposition, in which heat is released into the environment, actually occurs in clouds, in cold clouds. In this case, it's quite often that water vapor is deposited directly into solid ice crystals in cloud. So in other words, to go from a solid to gas, you are adding latent heat into the system. And if you're going from a vapor towards a solid, you will be releasing latent heat into the environment and taking it away from the water molecules. So let's take a closer look at phase changes in latent heat by, in our mind at least, melting a cube of ice. You see over here we're below freezing, below 0 degrees centigrade or Celsius, and we have a cube of ice. Add a little bit of heat to that, and the ice starts melting. When ice melts, the temperature won't go above 0 degrees Celsius. Once all the ice is melted, and everything's liquid, then the whole system starts increasing in temperature again until you get to 100 degrees Celsius. At that point, the water starts boiling, and the temperature doesn't go any higher than 100 degrees Celsius until all the water is transitioned into gas. At that point, any extra heat that you're adding will go into actually making these gas molecules go faster and faster, and you will actually increase the temperature of that gas. So this is a graph from your textbook, and we'll describe a little bit about what it shows. We start at the beginning here when we are not melting the ice cube, and we're actually heating the ice cube to 0 degrees Celsius. That represents this part of the graph. And since we're taking 1 gram of ice here, the temperature will, for each little bit of calories added here in terms of energy, right? And calories are sort of here along the x-axis. That will go into raising the temperature on the y-axis here, on this vertical axis here. So we start here in this area where we have ice only, and here we actually raise the temperature to 0 degrees Celsius. So at this point, the ice is melting. We're at this stage over here where we're melting the ice. In order to do that for 1 gram, that requires 80 calories. Okay, so during the time that we add those 80 calories over here, between 0 and 80, the temperature actually stays constant because all the energy is going into melting the ice. So with the next phase over here, where the water is completely in liquid form, and then the temperature resumes its increase until it gets to the boiling point here at 100 degrees. Again, this is called sensible heating because it's actually producing heat that you can sense with your finger. So finally, when you get to the boiling point over here, the liquid water begins to transition into gaseous form. So you'll notice as these 540 calories are added to the 1 gram of water, that the water gradually transitions into vapor. And by the end of this process, it should all be in gaseous form. So finally over here, you can see the water molecules are all free and in the form of a gas. And you can see that's represented here by the sensible heating of water vapor, because any additional heat you add will just go into increasing the temperature of the gas.